makes astronomy different from other types of science is that we can't perform experiments in the laboratory. So we have to look at the universe as we see it and create models to explain it. Astrophysicists regularly use supercomputers in their work, exploring our universe with a growing number of university groups now strictly dedicated to computational astrophysics. Let's explore how and why supercomputers are used and check out some of the incredible simulations underway around the world to uncover the secrets of our universe. The first supercomputer, the Cray 1, was built by Seymour Cray in 1976. People thought only a few of such supercomputers would meet the demand from science and engineering. At present, however, a laptop PC in your bag supersedes the computing power of the Cray 1. Supercomputers allow us to explore objects we'd otherwise be unable to see. We can use telescopes to view electromagnetic radiation, but there are many things we cannot see, even with the most high-powered and sophisticated modern observatories. Rather than trying to investigate the universe through observation, supercomputers use highly complex calculations to uncover phenomena that are otherwise hidden due to the structure of time and space. Astronomers have always explored how the universe appears. Theorists have always created ideas to explain how it came to look that way. Not until the computer age, however, could scientists studying the evolution of the entire universe match educated guesswork with the blueprint of observational evidence. My PhD supervisor was Professor George of Stathiou, who was then director of the Kavli Institute for Cosmology in Cambridge. Long before I was even born, George was a part of the science team in 1981, working on a survey of about 2,500 galaxies. At the time, an extraordinarily huge census of how the heavens looked on the largest of scales. The survey showed an early hint of what is today called the cosmic web, galaxies grouped in lengthy filaments of superclusters separated by vast empty voids. Theorists offered two competing ideas that might explain how matter could have coalesced in such a way. Both theories took into account the presence of dark matter, a mysterious substance that astronomers had come to accept as a necessary piece in the cosmic puzzle. The survey allowed astronomers to test these models, but only if they could figure out how to model the evolution of the universe over billions of years. Enter the Gang of Four, which included George. Although other astronomers had been working with n-body simulations, so called because they followed a number of points, n, each representing a concentration of mass, like a star or a galaxy. Their code couldn't handle such a large enough n to represent the large scales on the universe. George, however, suspected that a completely unrelated code used to simulate ionic microcrystals may work for galaxies too. Then, in a series of 5 landmark papers from 1985 to 1988, the team showed that observations of galaxies, clusters, filaments and voids were consistent with a simulated universe that had evolved under the influence of cold, dark matter, which is today one of the two key components in the standard cosmological model. The other is the acceleration due to the expansion of the universe, a discovery observers made in the late 1990s that George's simulations had anticipated. Nobody yet knows the exact nature of dark matter or dark energy, yet as more detailed and extensive observations of the universe have accumulated, these ideas have become the standard model of cosmology. Today, we believe our universe is composed of 5% ordinary matter, 23% dark matter, and 72% dark energy. Numerical simulations of the type pioneered by George show that a universe with this astonishingly precise yet remarkably strange composition does indeed develop structures which are a close match to those that we see around us. Supercomputers have been crucial in running these types of models and simulations since then, and have shed new light on the exotic models of the heavens. So what is a supercomputer? Well, when it comes to research, scientists are using supercomputers to address the world's biggest challenges, from modelling the global climate, to discovering alternate energy, to simulating aircraft, and more. The ability to process massive amounts of data in parallel has and continues to push the frontiers of science. Supercomputers are large systems specifically designed to solve complex challenges and require computing power and resources that go far beyond what is available in general-purpose computer servers. Until the 1990s, supercomputers were based on very high-end special-purpose components. This approach was very expensive and limited the use of supercomputers to a small number of research centres around the world that could afford it. To reduce the costs, researchers started to build supercomputers out of common off-the-shelf components, COTS for short, such as those used in general-purpose desktops and laptops. This shift greatly reduced the cost of each supercomputer, allowing many research centres and universities to acquire mid- and large-scale systems for a much lower cost than previously. Current supercomputers consist of a multitude of processors interconnected to a high-speed network. Each compute node features one or more multi-core, multi-threaded processor chips, several memory modules, network adapters, and local storage disks. The secret behind supercomputers is that they take advantage of a massively parallel architecture. A standard computer processor processes one instruction at a time, completing jobs in a distinct cycle of operation, one thing after the other. That's called serial processing. It's a bit like a person sitting at a supermarket checkout, picking up items from the conveyor belt, running them through the scanner, and then passing them on for you to pack in your bag. It doesn't matter how fast you load the items onto the belt or how fast you pack the carrier bags. The speed at which you check out your shopping is entirely determined by how fast the operator can scan and process the items in your basket, which is always one at a time. A typical modern supercomputer works much more quickly by splitting programs into pieces and working on many pieces at once. This is called parallel processing. It's like arriving at the checkout with a giant cart full of items, but loads of your mates with you. You split up the items between several friends. Each friend can go through a separate checkout with a few of the items and pay separately. Once you've all paid, you can get together again, load up the cart, and leave. The more items there are, and the more friends you have, the faster it gets to do things by parallel processing, at least in theory. Modern supercomputers employ several different modes of operation to take advantage of parallelism to achieve the highest performance possible. Some problems and algorithms are better suited for one type of parallel architecture versus another. Often when running programs on a supercomputer, a completely different algorithm will need to be written to take advantage of the hardware configuration. In 2004, an influential set of 7 classes of numerical methods commonly used on supercomputers were identified. These are known as the 7 dwarfs: dense linear algebra, sparse linear algebra, spectral methods, n-body methods, structured grids, unstructured grids, and Monte Carlo methods. These 7 classes of algorithms represent a large segment of supercomputing applications today, and many high-performance computing benchmarks are built specifically to target them. In a few decades, the strength of these giants has multiplied dramatically. In 1985, the most powerful supercomputer, the Cray 2, could process 1.9 billion floating point operations per second. That's like a single calculation, also known as a flop. 1.9 billion operations per second, 1.9 gigaflops. That's a huge number of calculations. By comparison, a current PS4 game console or a Microsoft Surface device reaches about 1.9 teraflops, almost 1,000 times more. Today there are at least 500 supercomputers in the world that can exceed a petaflop. A petaflop is 1 quadrillion, 1 million flops, huge number. The world's most powerful supercomputer today is called Summit, built by IBM for the US Department of Energy's Oak Ridge National Laboratory at Tennessee. It occupies the equivalent of 2 basketball courts and achieves an impressive 150 petaflops thanks to its 2.4 million cores. Your Surface device has either 4 or 8 cores. To achieve the same performance, you need about 75,000 Surface devices all connected together. Archer is the fastest UK national supercomputing service and is based just outside Edinburgh. The Archer hardware consists of about 5,000 compute nodes, each with 2 12-core Intel Ivy Bridge series processors, giving a total of about 120,000 processing cores. Each node has about 128 gigabytes of memory, and it can theoretically reach 2.5 petaflops. One famous example of a public supercomputer is the Galaxy Zoo project, a crowdsourced astronomy project which invites people to assist in the morphological classification of large numbers of galaxies. It is an example of citizen science at its finest, and enlists the help of members of the public to help in scientific research. A key factor leading to the creation of the project was the problem of data deluge, where research produces sets of data so vast that research teams are not able to analyze and process much of it. Kevin Sharansky, the astrophysicist at Oxford University and co-founder of Galaxy Zoo, described the problem that led to Galaxy Zoo's creation. When he was set the task of classifying the morphology of more than 900,000 galaxies by eye. I classified 50,000 galaxies myself in a week, and it was mind-numbing, he said. Another co-founder of the project commented that when Galaxy Zoo first started, the science team hoped that 20 to 30,000 people would take part in classifying the million galaxies that made up the sample. It had been estimated that a perfect graduate student working 24 hours a day, 7 days a week, would take 3 to 5 years to classify all the galaxies in the sample once. However, in the first version of Galaxy Zoo, more than 40 million classifications were made in 175 days by more than 100,000 volunteers. One advantage of taking part in these projects is that you get to see parts of space that have never been seen before. These images were taken by a robotic telescope, so the odds are that when you log on, that first galaxy you see will be one that no human eyes have ever seen before. In 1995, computer scientist David Geddy had an idea that could only originate at a cocktail party. What if the world's personal computers were linked together on the internet to create a virtual supercomputer that could help with the search for extraterrestrial intelligence? The network would be able to sort through the massive amounts of data being collected by radio telescopes, seeking signals that might point to an alien civilization around another star. A distributed supercomputer sounded outlandish at the time, but within 4 years, Geddy and his collaborators had built the software to make it a reality. They called it Seti at Home. Seti is a scientific mission whose goal is to detect intelligent signals from life outside Earth. One approach, known as radio Seti, uses radio telescopes to listen for narrow bandwidth radio signals from space. Such signals are not known to occur naturally, so a detection could provide evidence of extraterrestrial technology. With over 5 million participants worldwide, it's the distributed computing platform with the largest number of participants to date. It was acknowledged by the 2008 edition of the Guinness World Records as the largest computation in history. The world's fastest supercomputer has been created from volunteers loaning spare time on their home PCs to fold proteins, a scientific task that could prove instrumental in the fight against coronavirus. According to Folding at Home, the organization that runs the distributed computing effort, the combined power of the network has now broken through 1 million operations per second, or 1 exaflop. That made it 6 times more powerful than the current world's fastest traditional supercomputer, the IBM Summit. Last week it had more than doubled that, hitting a new record of almost 2.5 exaflops, faster than the top 500 traditional supercomputers combined, thanks to almost 1 million new members of the network. The breakthrough reflects a huge spike in support for the Folding at Home project. Backers run a simple piece of software on their home computer, which then downloads and performs small tasks to help determine the physical structure of proteins. What about supercomputers at the other end of the scale? One Raspberry Pi can make a nice web server, but what happens if you put more than 1,000 of them together? At Oracle's Open World convention in 2019, the company showed off a Raspberry Pi supercomputer that combined over 1,050 Raspberry Pis into one powerful cluster. When Oracle were asked why they chose to create a cluster of Raspberry Pis instead of using a virtualized server, one company rep simply stated, "Well, a big cluster's cool. That's good enough reason for me." Raspberry Pi clusters aren't practical when it comes to performance, but the novelty of supercomputer projects often makes the learning experience more worthwhile. We don't expect this product to go commercial, but it is a really cool example of just what you can do with a £25 computer. Let's look at a few different ways that these supercomputers are being used around the world in astrophysics, starting with n-body simulations. A simulation of n objects and their interactions over time. Things in the universe are subject to 4 fundamental interactions: strong nuclear, weak nuclear, electromagnetic, and gravitational forces. The first 2 forces only really act at incredibly short subatomic distances. Gravitational interactions between masses and the electromagnetic interaction between charges are examples of long-range forces. For cosmic simulations, where bodies are stars and galaxies, the interactions are all gravitational in nature, as the other forces are so small relative they can be ignored. In the last year, scientists have created an important new simulation of cosmic evolution. It takes place in a virtual cube 350 million light years in size and spans a time period from 12 million years after the Big Bang to the present day, or about 13 billion years worth of cosmic evolution. The project, called Illustris, encompasses over 12 billion data points to track the rise and evolution of some 50,000 galaxies. The simulation uses a total of 8,000 processors, equivalent to 2,000 years of processing time on a standard desktop computer. The run created 0.5 petabyte of data, and the end result is a model that not only recreates the emergence of stars and galaxies, but also the influence of dark matter and the spread of heavy metals throughout the universe. In a similar project, researchers from the University of Zurich have simulated the formation of our entire universe with a large supercomputer. A gigantic catalogue of about 25 billion virtual galaxies has been created from 2 trillion digital particles. The catalogue is being used to calibrate the experiments on board the Euclid satellite that should be launched perhaps this year or next, with the objective of investigating the nature of dark energy and dark matter. Thanks to the high precision of their calculations, featuring a dark matter fluid evolving under its own gravity, the researchers have simulated the formation of small concentrations of matter called dark matter halos, in which galaxies like the Milky Way form. The challenge of this simulation was to model galaxies as small as 1/10 of the size of our Milky Way, in a volume as large as the entire observable universe. Looking at some of the most powerful events in our cosmos, a new model is bringing scientists a step closer to understanding the type of light signals produced when 2 supermassive black holes collide. Millions or billions of times as the mass of the Sun, spiral towards a collision. For the first time, a new simulation fully incorporates the physical effects of Einstein's general theory of relativity, and shows that gas in such systems will glow predominantly in the ultraviolet and X-ray light. Just about every galaxy the size of our Milky Way or larger contains a monster black hole at the center. Observations show that galaxy mergers occur frequently in the universe, but so far no one has seen a merger of these giant black holes. Scientists have detected merging stellar mass black holes, smaller ones, which range from around 3 to several dozen solar masses, using the National Science Foundation's Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Gravitational waves are space-time ripples travelling at the speed of light. They are created when massive orbiting objects like black holes and neutron stars spiral together and merge. Supermassive mergers will be much more difficult to find than their stellar mass counterparts. One reason ground-based observatories can't detect gravitational waves from these events is because Earth itself is too noisy, shaking from seismic vibrations and gravitational changes from atmospheric disturbances. The detectors must be in space, like the proposed Laser Interferometer Space Antenna LISA project, led by the European Space Agency and planned for launch in the 2030s. Observatories monitoring sets of rapidly spinning super-dense stars called pulsars may detect gravitational waves from monster mergers. Like lighthouses, pulsars emit regularly timed beams of light that flash in and out of view as they rotate. Gravitational waves could cause slight changes in the timing of those flashes, but so far studies haven't yet made any detections. This supercomputing simulation depicts the gas in and around an evolving galaxy over 13 billion years ago. The purple to yellow colours indicate the gas density, with the purple tracing lower density gas and the yellow tracing higher density gas. The blue to red colours indicate gas temperature, the redder colours tracing the hotter gas, the bluer colours tracing the colder gas. And this shows the flows of cosmic filaments that are forming in the galaxy. When stars blow up as supernovae at the end of their lives, they drive galactic superwinds from the galaxy. These are seen predominantly as hot, diffuse gas blowing out of the galaxy. As there is more star formation and thus more supernovae at early times, these winds become calmer as the galaxy evolves. This visualization shows data from the Figuring Out Gas and Galaxies in ENSO project, also known as FOGGY, run on NASA's Pleiades supercomputer from researchers at the Johns Hopkins University. They're exploring supernovae. Supernovae are the spectacular explosions that occur in dying stars, which hold the answers to many questions about the origins of life. The cataclysmic events are responsible for spreading throughout the universe the chemical elements formed within stars. Researchers in the US have been trying to build models of these explosions to understand why there's more of one type of chemical element than another. Why is gold rare? Why is there iron in our blood and not something like copper? Why is there a difference between the amount of nitrogen and oxygen that we have in the atmosphere? The world's fastest supercomputer allows astronomers to create simulations that can model the nuclear burning of more isotopes of different elements than ever before. Nuclear burning is the fusion process that continues after a supernovae explosion. Nuclei combine, transmute into one kind of matter, into another kind of matter, and then release that into space. Eventually, the work will enable researchers to better understand the matter in the interior of a star, which can be dense enough to pack the collective weight of every human on Earth into a cubic centimetre of material. When the team finished their first simulation on the Summit supercomputer, they expect to have a database of accurate data on the exact makeup of a supernova explosion. That data can potentially be compared to observations from optical and gamma ray telescopes. and to data on elements collected from meteorites that have fallen to Earth. Observations of the relic radiation from the Big Bang, the cosmic microwave background, or the CMB, from the ground, balloons, and from space, has revolutionized our understanding of the universe by providing precise measurements of fluctuations generated in the very early universe. The data has allowed clean tests of fundamental physics at energy scales over 10 orders of magnitude higher than those achievable in particle accelerators like CERN. The Planck Surveyor satellite was an approved European Space Agency mission launched in 2009. It scanned the whole sky over a broad range of frequencies with unprecedented angular resolution and sensitivity. 3 Cambridge University departments formed the Planck Analysis Centre, bringing together a wide range of expertise in theoretical astrophysics, cosmology, and data analysis. I was part of the Planck HFI team, and we had primary responsibility for the high-level data analysis. The work included removal of contaminant foregrounds, such as galactic dust and extragalactic point sources, and a production of cleaned real space maps and power spectra of the temperature and polarization anisotropies. This computationally intensive work was run on the Cosmos supercomputer, which was proposed in 1997 by a consortium of leading UK cosmologists, brought together by the late Professor Stephen Hawking. The project is expected to receive a boost from the deployment of the European Space Agency's Euclid probe in a few years' time, which is scheduled for launch, supposed to be this year, maybe next year, maybe a bit longer. The mission will measure the shapes and redshifts of galaxies, looking 10 billion years into the past, thereby helping scientists to understand the geometry of the dark universe, i.e., how dark matter and dark energy influence it as a whole. This map will be created using the facility's supercomputer located in Cambridge's Department of Applied Mathematics and Theoretical Physics. Currently, it is the largest shared memory computer in Europe. So what is the future of supercomputing? Supercomputing has the potential to be the underlying layer to support solutions for many of the world's most pressing contemporary challenges. Global privacy, identity issues, stalemates in medical research, sustainable supply chain logistics, just to name a few. As Albert Einstein said, we can't solve problems by using the same kind of thinking we used when we created them. Technology hasn't created all of the problems, but it could help to provide some of the answers. If we extrapolate to 2040, what might be expected? Will Moore's law about the exponential expansion of semiconductor technology continue up to this point? If the exponential growth continues, supercomputers will be running at the zettaflops level, giving us 10 to the 21 operations per second. Zetascale computing promises exciting advances in many diverse fields: personalized medicine, genomics, cancer capture, astrophysics, market economics, biofuel, blockchain, cryptography, just to name a few. I think a complete simulation of a human brain will be possible in our lifetimes. And perhaps, more importantly, zettaflop computers should be able to accurately predict the entire weather system at least 2 weeks in advance. That'd make a change. Predicting the weather, exploring the edge of our universe, and creating a more energy-smart power grid are exciting reasons to keep your eyes on the world of supercomputers.